In this lecture and next lecture, we will discuss the role of quantum transport in electrical metrology, or the quantum, which generally referred to as the quantum electrical metrology. So, metrology is the science of measurement and its applications. By definition, it includes all the theoretical and practical aspects of measurement, no matter what the uncertainty of the measurement and the area of application. And internationally, the units and these standards are controlled by a body, International Bureau of Weights and Measures, which is also called BIPM, which is an intergovernmental organization through which the member states act together on matters related to measurement science and measurement standards. So, in this lecture, what we will do is we will look at how the units or standards of electrical measurements, such as the voltage, resistance, and current. These are the three major electrical base units. How these units are standardized against fundamental constants using various quantum electrical phenomena that we have uh, gone through during the course of this series of lectures. So in this lecture, we will look at the quantum Hall effect resistance standard and the Josephson effect voltage standard. In the next lecture, we will look into the current standard and also the quantum electrical metrology triangle. Okay. Now, the SI, or the system of units, um, under has undergone a major revision in 2019, very recently, where the units defined in terms of fundamental constants. Okay, these constants are the second, which is defined as a fixed numerical value using the ground state hyperfine structural transition frequency of cesium 133 atom, delta nu Cs, which is equal to this hertz. Okay, so second is inverse of that. And then speed of light is another fundamental constant, which is taken to be this fixed numerical value. Planck's constant, the charge of electron or elementary charge, Boltzmann's constant, Avogadro number, and luminous efficacy, KCD, of monochromatic radiation of this frequency is taken to be this fixed numerical value. So in 2019, what happened to the metrology is every unit are defined using this fundamental set of fundamental constants. Okay, and there are 7 base units: time, length, mass, electric current, the thermodynamic temperature, which is Kelvin, and mole, and luminous intensity, unit is candela. These are the 7 base units which are defined by the definition which is given on the left hand side. And you can see everything is defined in terms of these numerical constants. And the 4 base units which has undergone major revision in 2019 are these: the mass, electric current, Kelvin, and more. And out of these 4, what attracts our interest is the electric current, ampere. So we will define how the ampere is defined in the post 2019 revision, and how it was defined before that in the next lecture. But it is quite interesting to note that current is the only electrical quantity which enters in the base unit, and that is the one which has been ill-defined so far, which is kind of really, really strange and surprising. Okay, and in 2019, it has been redefined using fundamental constants. Okay, that we will discuss in the next lecture. Okay. Now let us look into how the other 2 major electrical quantity, that is the voltage and the resistance, are defined. Okay, the resistance is standardized using quantum Hall effect. Quantum Hall effect we have gone through in great detail in one of the previous modules. So in a nutshell, the resistance of a 2-dimensional system shows quantized plateaus, or the conductance shows quantized plateaus versus B field. And the resistance values for these plateaus are given by this formula. For H by E squared is the resistance, quantum limit of resistance, and divided by 1 by n. So these are the resistance values, and n is the plateau index, or plateau number. And what we are measuring is the Hall resistance. The current is, if the current is in this direction, we are measuring V1 minus V3 or V2 minus V4. That's the Hall resistance. And there is a universality for this quantum Hall resistance. It has been measured over various materials, or device on various materials, various systems, various places, but the error in the quantized resistance value, delta RH, is in the range of nano ohm per ohm. So in this case, what is being measured is the resistance of the second plateau and the fourth plateau for devices of the various widths. So it's 200 micrometer, 10 micrometer, 50 micrometer, various widths, and the error in the plateau resistance value is in nano ohms. And in this specific case, what is being measured is the resistance for 2 different devices as a function of temperature. And the thing that we need to note here is that the voltage probes are non-symmetric. It's not exactly symmetric, it's slightly off. But that still is not going to play a major role. You can see that still the error is in nano ohm. And as the temperature is increased, the error is actually decreased up from vary the temperature from a few millikelvins to 1.2 Kelvin, little over a Kelvin. So as a function of temperature also, there is not much deviation for this resistance. And in this third case, it's measured as a function of carrier concentration. It's on a silicon MOSFET geometry. And when you vary the gate voltage, you're going to change the carrier concentration. And even as a function of carrier concentration, the Hall resistance is not showing much of a variation. You can see still it's nano ohm. That means the value of Hall resistance is universal, and the variation is only in the ninth place after the decimal. So in nano ohm per ohm, that is the variation that you are seeing. So this quantum Hall resistance standards have been now used to standardize the resistance values over many years now, and that is now well approved as the quantum standard for resistance. And as you can see, these are majorly done on bulk two-dimensional materials such as silicon two-dimensional electron gas or gallium arsenide, aluminum gallium arsenide two-dimensional electron gas. And you can see the temperature ranges that these materials would show this quantum Hall effect is in Kelvin or sub-Kelvin range. So now there are new generation of two-dimensional materials which would show this quantum Hall effect at higher temperature. And now the current technology has been now geared towards observing this quantum Hall effect at higher temperature and on simpler systems. These systems are complicated in terms of technology-wise, in terms of getting these materials made. But the new generation of two-dimensional system, mainly the graphene, is very easy to obtain, and it's very easy to fabricate devices on graphene. And now the field is more looking into that direction, where how can you use graphene as the resistance standard. So in this work, what they have done is they have used a graphene sample in the whole bar geometry, and of course measured the quantum Hall effect. And they are comparing that against a gallium arsenide material, which is a blue curve here. As you can see in the red curve, you see very extended wide plateau range. For this is for n is equal to 2, the second plateau. The resistance is 12.45 kilo ohm, and this is accurate down to nano ohm or nano ohm range, or accurate down to the power -9. Okay, and as you can see, compared to gallium arsenide, the plateau is pretty wide. Okay, and this measurement is around 1.3 Kelvin, and you can see that the graphene sample, even at 100 Kelvin, that is little over the liquid nitrogen temperature, that is the dashed line here still showing the plateau behavior. Okay, so what that means is these graphene based samples can be used for this metrology purpose, operating at a really high, much higher temperature, which makes the whole technology a lot easier to handle. In this plot, what you are seeing is the accuracy of this graphene resistance standard. So you are comparing the graphene with gallium arsenide, how much the variation is there for resistance of this graphene sample for a particular quantum Hall plateau as opposed to gallium arsenide. And you can see that it's pretty close to zero, very close to zero, like a nano or 10 to the power -9 range. Okay, 9th place after the decimal. And that has been compared for also for various temperature, okay, and for running various currents through it. And you can see that in all these cases, the quantization of this resistance is pretty robust, and the error is really low. So that is kind of the current technology where people have now started exploring and also using graphene as the resistance standard as opposed to the conventional gallium arsenide, aluminum gallium arsenide structure, which makes the technology a lot more easier to handle. Okay. The next important or fundamental electrical quantity is the voltage. So the voltage is standardized using another quantum transport phenomena, that is the Josephson effect, especially the AC Josephson effect. So we have done this topic also in somewhat in great detail. So what you have is you have the Josephson equation. When you apply a DC voltage V across a Josephson junction, which consists of two superconductors separated by a thin layer of insulator, okay, then the AC current will flow with a frequency given by 2E by H V, where V is the voltage. And the frequency that you are going to get out of the small DC voltage that you are applying is close to 483.6 megahertz per microvolt. That is, if you apply 1 microvolt, the frequency that the junction is going to emit, the AC current that you are going to get is 483.6 megahertz. That is for 1 microvolt. Now we have learned one more associated phenomena, that is the inverse AC Josephson effect, or sometimes that is also referred to as AC Josephson effect. That is when you have an AC plus DC bias across the junction. In this case, you have only DC, but now you are doing an AC plus DC. AC is with certain frequency F, and DC you are varying. Now, this phenomena says the junction oscillation, because the DC, okay, that is going to phase slopes to the applied frequency whenever this condition is met. That means you have a AC frequency applied on the junction and you are sweeping the DC voltage. Whenever this condition is met, there will be phase lock, and that will make a current run through the junction. A DC current, okay. Normally, if you apply only AC, then what you get is nothing. Okay, when you apply only AC, you don't get any DC current. Okay, if you apply DC voltage, you get an AC current. But when you apply AC plus DC, and when this condition is met, you will get a DC current through it. Okay, so the effect is such that the average voltage across the junction is H by 2 into F, where F is the frequency. Now we can see that the voltage V is, this is the voltage across the junction. That voltage is only a function of two fundamental constants and frequency. And frequency is something you can very accurately define in metrology. Very, very accurately you can define and measure and apply. Okay. All metrology standard works in that assumption, and that is pretty true. Okay. So what this says is, because of this phase locking, you will see constant voltage steps whenever this condition is met or this condition is met. Okay. Not only for this specific frequency, this is going to happen also for the overtones. Whenever the voltage matches with any of the harmonics of that frequency, that is n into h by 2e into f. Okay, that you have certain frequency applied and you sweep the voltage. Okay, whenever that voltage is h by 2 into f or any harmonics of that, then you would observe a step in the current at voltages defined by this value. So you are going to see current flowing through the DC current flowing through junction for this value. So you will see steps where n is an integer. Okay, and this 2e by h is called Josephson constant Kj. That is given by this value. Okay, this is 483.596, you can say, megahertz per microvolt, or this much gigahertz per volt. Okay, that's what it is. Okay. This is the same number. It has been rounded 2.6 here, but the same number. Okay. What that means is when you have no AC voltage applied, you will get a curve which looks like this. This is your simple IV characteristic for a Josephson junction. The moment you turn on the frequency, you will see steps in voltage. Okay. And each of the step is given by this equation or given by this number. Okay. So here you can very accurately tell that the voltage steps are given by this equation, which depends only on two fundamental constants and the frequency. And the assumption, as I told, is frequency is something you can very accurately apply, determine, or measure. Okay, that is the premise that the whole this Josephson voltage standard work. And usually, even though this is a symbolic representation for this voltage stand, this Josephson junction, usually what you have is you have a layer or a film of a superconducting material, then you have a layer of insulator, then you have another superconducting material, and you are going to apply the AC and DC voltage in this manner as shown in this diagram. Voltage steps that you observe in an AC Josephson effect, those are called Shapiro steps, which was observed by Shapiro in 1963 in a landmark experiment with the Josephson junction of aluminum oxide and tin. So when he applied 9.3 gigahertz, he got a smaller steps compared to when he applied 24.85 gigahertz. These are constant voltage steps that is observed in that experiment. In another experiment recently, a niobium Josephson junction, which was biased at 20 gigahertz, showed steps in voltages close to 5 microvolt. I mean, I'm not saying the accurate voltage here, but something like constant voltage steps approximately 5 microvolt. So you can see that when no voltage, when no frequency was applied, no RF was applied, there are no steps. You will see the current voltage characteristics of a typical Josephson junction. And the moment you turn on the RF, you will see well-defined, really flat steps in voltage, which is in the y-axis here, which correspond to, or which is defined by this equation here. Now, practically, the voltage produced by single junction is really small. And if you look at the equation, 1 microvolt correspond to half a gigahertz or 500, close to 500 megahertz. So if you apply if you apply 1 gigahertz, you will get close to 2 microvolt. And if you want an appreciable voltage like a few hundreds of millivolt, you will be applying really high frequency, hundreds of gigahertz, which is practically not easy. It's almost impossible to work with. Especially you have the superconductor junction, which is sitting at a really low temperature and pumping really high RF voltage with a very high frequency RF signal into this creation. It's not an easy business. So what is practically done is you make an array of these junctions. Here is an example where you have an array of the Josephson junction, one-dimensional arrays or two-dimensional array. And when you apply RF plus DC onto these, then you can add these voltages because this is like a battery. Okay. That is how you produce Josephson junction voltage standard, which will give you higher voltages. In this case, what you have is you have 20,000 junctions, which is eventually giving you 10 volt Josephson voltage standard. Here what you have is like 5 million junctions, is giving you 20 volt Josephson voltage standard, JVS. So the advantage of having larger number of junctions is you can work with lower frequency, which is easy to handle, technologically, because the voltage is proportional to basically the frequency and also the number of junctions, because those are in series. So if you have more junctions, you can actually get away with lower frequency to get an appreciable voltage, which you can measure without much error. So that is the point here. So the current generation of Josephson junctions are basically large arrays, which consists of tens of thousands to million junctions, which are fabricated uniformly. That is also technologically challenging, but that is much easier to deal with compared to the engineering problems of dealing with really high frequency microwaves. Okay. Now let us take a quick look at the accuracy and universality of the Josephson effect. It is given by this equation, and as you can see, the voltage has only 3 terms there. That is, of course, N is a number, F is also a number because it's a frequency. That is very easy to control, okay, and calibrate. And H is a fundamental constant, and E is also a fundamental constant. The voltage definition involves only fundamental constants and frequency. It does not involve any other material parameters. So you can use any system. It doesn't depend upon whether you use niobium, aluminum, tin, lead, it doesn't matter. Okay. In a very famous experiment, they have compared 2 Josephson junctions. Both of them are phase locked by the same frequency, but they are completely independent Josephson junction. Okay. So this is going to produce a Josephson voltage across it. This is going to produce a Josephson voltage across it. These are different views of that. This is the side view and this is the top view. And what we have is, you can consider this a battery because it's a Josephson junction is a battery. It's going to give you a DC volt. This is also going to DC volt. Any difference between these two is going to have a current flowing through this loop. And that current would be picked up by an RF squid. The squid is a really sensitive detector for really small magnetic field. So this current is going to give you a magnetic field that will be coupled to this pickup coil for this squid. So in this experiment, they inspected whether there is any current flowing through this loop, which would result from the difference in the Josephson voltage, which is driven by the same microwave source. and actually they couldn't measure anything. This is a really small number. Okay, the average voltage difference is basically 10 to the power minus 21 volt. That is immeasurable. Or the accuracy of this proportionality constant Kj. Kj is the fundamental constant here. F is something which you give. Okay, so compare the accuracy of this proportionality constant, Josephson constant, that is 2% in the power 16. But it's some way beyond what you can imagine. So they couldn't detect, you can say for safely, that they couldn't detect any change, any difference between the voltages produced by these two junctions. And in another experiment, they have also inspected long-term stability of this voltage standard. And that's again like in nanovolt range. Okay, voltage difference basically between compared to between the two junctions, that is again in nanovolt range in long-term stability. What that means is this Josephson effect is universal and accuracy is something beyond what you can expect for many of these, any of the other effects that you have around. And that is why this Josephson effect is used as a standard for voltages. So all the voltage sources or the voltage that you see are standardized using this Josephson effect or AC Josephson effect.